May 1945. Germany is defeated. American forces sweep through German territory. In a hidden airfield deep in the German countryside, American soldiers discover something that defies belief. A sleek fighter aircraft unlike anything they have ever seen. No propellers, no piston engines, something completely different. The aircraft is called the Me-262, the Messerschmitt 262, and it represents the future of aviation. American military officers examine the aircraft carefully. They examine the engines, and they cannot believe what they are seeing. These are not conventional engines, these are jet engines. Completely different technology, revolutionary technology, technology that Germany had developed in secret. Technology that could change aerial warfare forever. American engineers realize in that moment that aviation technology has taken a leap into the future. Germany had achieved something that America was still trying to develop. Germany had built jet-powered fighter aircraft, while American designers were still perfecting propeller-driven aircraft. One German jet could outrun 10 American fighters. One German jet could climb faster. One German jet represented aviation technology that was years ahead of American aviation. One German jet showed American military planners that the future of air combat belonged to jet engines, not piston engines. This is the story of the Me-262 Messerschmitt. This is the story of how American engineers captured German jet technology. This is the story of how a single captured aircraft changed the entire direction of American aviation development. The dream of jet propulsion was not unique to Germany. Aviation engineers around the world understood that conventional piston engines and propellers were reaching the limits of their capability. Piston engines could only push aircraft so fast. Propellers became less efficient at high speeds. As aircraft flew faster, conventional propulsion systems became increasingly inefficient. Aviation engineers understood that a fundamentally different propulsion system would be necessary to achieve the next level of aircraft performance. The concept of jet propulsion was based on a simple principle. A jet engine would compress air. The compressed air would be mixed with fuel and ignited. The burning fuel would heat the compressed air. The heated air would expand rapidly. The expanding air would be expelled through a nozzle at the rear of the engine. The expelled air would create thrust that would propel the aircraft. In theory, the concept was elegant. In practice, building a jet engine that actually worked was extraordinarily difficult. The engine had to compress air to high pressure. The engine had to withstand extreme temperatures. The engine had to operate reliably. The engine had to produce sufficient thrust to propel an aircraft. Aviation engineers in Britain began developing jet engines in the 1930s. British engineer Frank Whittle conducted pioneering work on jet engine development. Whittle built experimental jet engines. Whittle tested his engines. Whittle demonstrated that jet propulsion was technically feasible, but the British military did not immediately commit to jet aircraft development. British military planners were skeptical about the reliability of jet engines. British military planners were concerned about the operational challenges of jet aircraft. British military planners were focused on improving conventional fighter aircraft. In Germany, aviation engineers were also investigating jet propulsion. German engineers understood that jet propulsion offered advantages over conventional piston engines. German engineers were willing to invest in jet engine development. German engineers were willing to accept the risks and challenges of developing revolutionary aviation technology. The German aircraft manufacturer Heinkel began investigating jet propulsion in the late 1930s. Heinkel designers worked with engineers from Junkers to develop a jet engine. The Junkers company, which had extensive experience building aircraft engines, developed what would become known as the Jumo 004 jet engine. The Jumo 004 was one of the first practical jet engines. The Jumo 004 used an axial flow compressor. The compressor had multiple stages. Each stage compressed the air further. The compressed air passed into a combustion chamber where fuel was injected and ignited. The hot exhaust gases passed through a turbine. The turbine extracted some of the energy from the exhaust gases. The remaining energy drove the aircraft forward. The Jumo 004 was revolutionary, but the Jumo 004 was also crude compared to what later jet engines would become. The Jumo 004 had a limited service life. The Jumo 004 often overheated. The Jumo 004 was unreliable. But it worked. The Jumo 004 produced thrust. The Jumo 004 was a working jet engine. Heinkel used the Jumo 004 engine in an experimental aircraft called the He-178. The He-178 first flew in August 1939. The flight was remarkable. The He-178 was the first aircraft powered by a jet engine to achieve flight. The He-178 demonstrated that jet-powered flight was possible. The He-178 was not designed as a weapon. The He-178 was an experimental aircraft. The He-178 was designed to prove that jet propulsion was technically feasible. But the He-178 demonstrated that jet aircraft were the future of aviation. German military leadership recognized this. German military leadership authorized development of a jet-powered fighter aircraft. German military leadership authorized the development of the Me-262 Messerschmitt. The German aircraft manufacturer Messerschmitt began designing a jet-powered fighter aircraft in the early 1940s. The aircraft that emerged from this design process was the Me-262. The Me-262 was designed to be a fighter aircraft. The Me-262 was designed to engage enemy aircraft in aerial combat. The Me-262 was designed to be faster than any existing aircraft. The Me-262 was designed to climb faster than any existing aircraft. The Me-262 was designed to have superior performance to any piston-engine fighter. The Me-262 was powered by two Jumo 004 jet engines. Two engines provided more thrust than one engine. Two engines provided redundancy. If one engine failed, the aircraft could potentially return to base on the other engine. The Me-262 airframe was sleek and efficient. The fuselage was streamlined. The wings were swept back. The swept-back wing design reduced aerodynamic drag at high speeds. The swept-back wing design was revolutionary. Most aircraft of that era had straight wings. The Me-262 was one of the first military aircraft with swept-back wings. The Me-262 was armed with four 30mm cannons. The cannons were mounted in the nose of the aircraft. Four cannons provided devastating firepower. A burst from four 30mm cannons could destroy an enemy aircraft with ease. The Me-262 was revolutionary in every way. The Me-262 had jet engines. The Me-262 had swept-back wings. The Me-262 had high-speed capability. The Me-262 had powerful armament. The Me-262 was a weapon that seemed to come from the future. The development of the Me-262 took longer than German military planners hoped. The Jumo 04 engines were unreliable. The engines would overheat. The engines would fail. Developing reliable jet engines proved to be extraordinarily difficult. Messerschmitt engineers worked intensively to solve the problems with the Me-262. Engineers tested different air intake designs to ensure smooth airflow to the engines. Engineers worked with junkers to improve the reliability of the Jumo 004 engines. Engineers tested different fuel systems. Engineers tested different cooling systems. The development process was slowed by German military priorities. Resources that might have been devoted to Me-262 development were diverted to other aircraft and weapons programs. Factories that might have produced Me-262 components were damaged by Allied bombing. Raw materials that might have been used for Me-262 construction were diverted to other military programs. Despite these challenges, the Me-262 development continued. By 1943, the first Me-262 prototypes were flying. The prototypes demonstrated that the design was sound. The prototypes demonstrated that jet-powered fighter aircraft were operationally feasible. By 1944, the Me-262 was ready for combat. The first operational Me-262 units were formed. German pilots began flying the Me-262 in combat against Allied aircraft. The Me-262 was revolutionary in combat. The Me-262 was faster than any Allied fighter. The Me-262 could climb faster than any Allied fighter. The Me-262 could dive faster than any Allied fighter. American P-51 Mustang pilots, who were flying the best piston-engine fighters in the world, found themselves outclassed when they encountered Me-262s. The P-51 could not catch a Me-262 in a dive. the P-51 could not climb as fast as a Me-262. The P-51 could not match the performance of the Me-260. German Me-262 pilots realized this. German pilots understood that their aircraft had a tremendous performance advantage. German pilots used this advantage to devastating effect. Me-262 pilots would approach from high altitude. Me-262 pilots would dive on American bombers or fighters. Me-262 pilots would fire their cannons. American aircraft would be destroyed. American military commanders were alarmed by the appearance of Me-262s. American military planners realized that a new type of aircraft had appeared on the battlefield. American military planners realized that jet-powered aircraft represented the future of air combat. But the Me-262s appeared too late in the war. Germany did not have enough Me-262s. Germany did not have enough trained pilots. Germany did not have the industrial capacity to produce Me-262s in the numbers needed to affect the outcome of the war. The Me-262 was a revolutionary weapon, but Germany could not produce it in sufficient quantities to change the course of the war. Nevertheless, the Me-262 demonstrated that jet-powered aircraft were operationally feasible. The Me-262 demonstrated that jet aircraft could defeat piston-engine aircraft. The Me-262 demonstrated that the future of air combat belonged to jet-powered aircraft. As American forces advanced through Germany in 1945, American military planners made it a priority to locate and capture Me-262 aircraft and Me-262 production facilities. American forces eventually discovered a hidden airfield where several Me-262 aircraft were being stored. American soldiers carefully secured the aircraft. American military officers realized that these aircraft represented revolutionary aviation technology. American military planners understood that studying the Me-262 would be important for American aviation development. The Me-262 aircraft were carefully preserved. The aircraft were protected from damage. The aircraft were transported to American military facilities for detailed examination. American aviation engineers and military specialists examined the Me-262 aircraft in meticulous detail. Different teams of engineers examined different aspects of the aircraft. One team examined the airframe. Another team examined the engines. Another team examined the control systems. Another team examined the weapon systems. Another team examined the electrical systems. American engineers took detailed measurements. American engineers made detailed sketches. American engineers photographed every component. American engineers understood that they were examining aircraft technology that represented a revolutionary advance in aviation. When American aviation engineers began examining the Jumo 004 jet engines from the Me-262, they were fascinated and impressed by the design. The Jumo 004 was a turbine-powered jet engine. The engine had an air intake at the front. The air intake directed incoming air into a compressor. The compressor had multiple stages. Each stage compressed the air further. The compressed air passed into a combustion chamber. Fuel injectors sprayed fuel into the combustion chamber. Igniters ignited the fuel. The burning fuel heated the compressed air to extremely high temperatures. The hot gases from the combustion chamber passed through a turbine. The turbine had blades that were forced to rotate by the expanding hot gases. The rotating turbine was connected to the compressor. The turbine drove the compressor. The turbine extracted energy from the hot gases that was used to power the compressor. The remaining energy in the hot gases was expelled through a nozzle at the rear of the engine. The expelled gases created thrust that propelled the aircraft forward. American aviation engineers had theoretically understood how jet engines worked, but seeing an actual functioning jet engine was different. American engineers examined the internal components. American engineers studied the materials used in the engine. American engineers studied how the engine was constructed. American engineers were impressed by the engineering solutions that German designers had developed. The way the turbine was designed to extract energy from the hot gases. The way the fuel injectors atomized fuel for efficient combustion. The way the engine was constructed to withstand extreme temperatures and pressures. American aviation companies like General Electric and Pratt & Whitney had been developing jet engines. But American jet engine development had been slow. American companies had theoretical designs but limited practical experience. Examining the Jumo 004 engine provided American engineers with practical knowledge about jet engine design and construction. American aviation engineers studying the Me 262 airframe were impressed by the design. The fuselage of the Me 262 was sleek and streamlined. The fuselage was designed for high-speed flight. The fuselage was designed to minimize aerodynamic drag. The wings of the Me 262 were swept back. Swept-back wings were revolutionary for that era. Most aircraft had straight wings. The Me 262 was one of the first military aircraft with swept-back wings. Swept-back wings reduced aerodynamic drag at high speeds. Swept-back wings allowed the aircraft to achieve higher speeds than would be possible with straight wings. American aviation engineers studying the Me 262 understood the significance of swept-back wings. American aviation engineers realized that swept-back wings would become standard on future high-speed aircraft. American aviation engineers began incorporating swept-back wing designs into American aircraft. The landing gear of the Me 262 was retractable. When the landing gear retracted into the fuselage, it reduced aerodynamic drag. Retractable landing gear was not unique to the Me 262. But the way the Germans had designed and implemented the retractable landing gear was well engineered and efficient. The cockpit of the Me 262 was designed for pilot visibility. The pilot had excellent forward visibility. The pilot could see around the aircraft with minimal obstruction. The cockpit design allowed the pilot to situate awareness of the surrounding airspace. American aviation engineers studying the Me 262 cockpit design understood that German designers had put thought into pilot ergonomics and visibility. American aircraft designers began incorporating similar principles into American aircraft design. American aviation engineers studying the Me 262 examined the control systems carefully. The control surfaces of the Me 262 included ailerons for roll control, elevators for pitch control, and a rudder for yaw control. These control surfaces were cable-actuated from the cockpit. The pilot controlled the aircraft through conventional control inputs. But the Me 262's control characteristics at high speed were different from piston-engine aircraft. The Me 262 could fly faster than any piston-engine fighter. At high speeds, aerodynamic forces on the control surfaces became very large. The pilot had to be aware of the effects of high-speed flight on aircraft handling. American aviation engineers understood that future high-speed jet aircraft would have similar control characteristics. American engineers began thinking about how to design control systems that would work effectively at high speeds. The fuel system of the Me 262 was designed to feed fuel to the two jet engines. The fuel system had to maintain proper fuel pressure and flow to the engines. The fuel system had to manage fuel distribution between the two engines. The fuel system had to handle the unique requirements of jet engines compared to piston engines. American aviation engineers studying the Me 262 fuel system learned about the specific requirements for fueling jet engines. American aviation engineers began developing fuel systems for American jet aircraft based on principles they learned from studying the Me 262. The Me 262 was armed with four 30mm cannons. The cannons were mounted in the nose of the aircraft. The cannons were fired by the pilot through electronic firing systems. 30mm cannons were large weapons for an aircraft. 30mm projectiles were devastating. A burst of fire from 30mm cannons could destroy an enemy aircraft. 4 cannons provided tremendous firepower. American aviation engineers studying the weapons system of the Me 262 were impressed by the integration of the weapons with the aircraft design. The cannons were mounted in a location that provided the pilot with good aiming capability. The cannons were integrated with the aircraft's fire control system. The ammunition storage for the cannons was located inside the fuselage. The ammunition was fed to the cannons through ammunition feeds. The ammunition storage provided sufficient ammunition for sustained combat operations. American aviation engineers understood that future jet fighters would need effective weapons systems. American aviation engineers began thinking about how to integrate weapons systems into jet aircraft designs. American aviation engineers compared the Me 262 to the best American fighter aircraft of that era, the P-51 Mustang. The P-51 Mustang was an excellent piston-engine fighter. The P-51 had excellent maneuverability. The P-51 had good climb performance for a piston-engine fighter. The P-51 had excellent range. The P-51 had good armament. The P-51 was arguably the best piston-engine fighter in the world. But the Me-262 was faster than the P-51. The Me-262 could climb faster than the P-51. The Me-262 could dive faster than the P-51. The Me-262 had better high-altitude performance than the P-51. American aviation engineers understood the implications. The P-51 represented the pinnacle of piston-engine fighter development. But the Me-262 had leapfrogged piston-engine technology. The Me-262 had entered a new realm of aircraft performance. American aviation planners understood that American fighters had to transition to jet propulsion. American aviation planners understood that piston-engine fighters were becoming obsolete. American aviation planners understood that future air superiority would belong to jet-powered aircraft. American aviation companies had been developing jet engines, but the development had been slower than German development. American aviation companies like General Electric and Pratt & Whitney had theoretical knowledge about jet engines. But American companies had limited practical experience. The discovery of the Me-262 and the Jumo 004 engine provided American companies with practical examples of working jet engines. American engineers could study the Jumo 04 and understand how German engineers had solved specific design challenges. American engineers studied the compressor design of the Jumo 004. American engineers studied how the turbine extracted energy from the hot exhaust gases. American engineers studied the materials used in the engine. American engineers studied the fuel injection system. American engineers studied the combustion chamber design. American engineers realized that German engineers had solved many of the design challenges that American engineers were struggling with. American engineers incorporated what they learned into American jet engine designs. American companies accelerated their jet engine development programs. American companies were confident that they could develop jet engines comparable to or superior to the German Jumo 004. American companies began producing jet engines for American aircraft. After studying the Me-262, American military planners accelerated the development of American jet fighters. The American aviation industry had several fighter aircraft designs in development. The North American F-86 Sabre was one of the most promising designs. The F-86 was powered by a jet engine. The F-86 had excellent aerodynamic design. The F-86 had swept-back wings inspired partly by understanding gained from studying the Me-262. The Lockheed F-80 Shooting Star was another American jet fighter. The F-80 was powered by a single jet engine. The F-80 was fast and maneuverable. The F-80 represented American capability in jet fighter development. Other American companies were also developing jet fighters. Republic Aviation was developing the F-84 Thunderjet. Convair was developing the F-106 Delta Dart. The American aviation industry was rapidly transitioning from piston-engine fighters to jet fighters. The influence of the Me-262 on American jet fighter development was significant. American designers understood the performance capabilities that jet engines made possible. American designers understood the aerodynamic principles that enabled high-speed flight. American designers incorporated these principles into American jet fighter designs. The North American F-86 Sabre became one of the most iconic American jet fighters. The F-86 was strongly influenced by design principles that American engineers had learned from studying the Me-262. The F-86 had swept-back wings. Swept-back wings reduced aerodynamic drag at high speeds. Swept-back wings allowed the F-86 to achieve high speeds. The F-86's swept-back wing design was inspired partly by the Me-262's wing design. The F-86 had an excellent aerodynamic design. The fuselage was streamlined for high-speed flight. The air intake was designed to provide smooth airflow to the jet engine. The overall shape of the aircraft was designed to minimize aerodynamic drag. The F-86 was powered by a Pratt & Whitney J-47 jet engine. The J-47 was a powerful jet engine. The J-47 provided the F-86 with excellent acceleration and climb performance. The F-86 had excellent maneuverability. The F-86 had powerful control surfaces that allowed the pilot to maneuver the aircraft effectively. The F-86 had excellent stability characteristics. The F-86 was armed with 650 caliber machine guns. The machine guns provided adequate firepower for air-to-air combat. The F-86 represented the culmination of American jet fighter development in the immediate post-war period. The F-86 was influenced by what American engineers had learned from studying the Me-262. The F-86 was a superb jet fighter that would see extensive use during the Korean War. The Soviet Union also studied captured German jet aircraft and jet engine technology. Soviet aviation engineers examined captured Me-262 aircraft. Soviet engineers studied the Jumo 004 jet engine. Soviet engineers incorporated what they learned into Soviet jet fighter designs. Soviet aviation designers developed the Mikoyan-Gurevich MiG-15 jet fighter. The MiG-15 was powered by a Rolls-Royce-derived jet engine. The MiG-15 had swept-back wings, inspired partly by understanding gained from studying German aircraft design. The MiG-15 became one of the most capable jet fighters of the era. The competition between American F-86 Sabre and Soviet MiG-15 during the Korean War drove rapid development of jet fighter technology. Both American and Soviet designs were influenced by German jet aircraft design principles. After World War II, jet engine development accelerated globally. American companies, Soviet companies, and British companies all pursued aggressive jet engine development programs. American companies like General Electric, Pratt & Whitney, and Allison continued developing jet engines. American companies incorporated design principles learned from studying the Jumo 004 into American engines. American jet engines became increasingly powerful and reliable. British companies like Rolls-Royce continued jet engine development. British engineers had been pioneers in jet engine development through Frank Whittle's work. British jet engines became increasingly sophisticated. Soviet companies developed jet engines based partly on understanding of German technology. Soviet jet engines became increasingly powerful and reliable. The competition between American, British, and Soviet jet engine manufacturers drove rapid development. The result was continuous improvement in jet engine performance, reliability, and efficiency. The development of jet engines for military aircraft eventually led to the development of jet engines for commercial aviation. De Havilland in Britain developed the Comet, the first commercial jet airliner. The Comet was powered by de Havilland Ghost jet engines. The Comet entered service in 1952. The Comet demonstrated that commercial aviation could transition to jet propulsion. Douglas Aircraft developed the DC-8, a four-engine commercial jet transport. The DC-8 was powered by Pratt & Whitney JT4 jet engines. The DC-8 entered service in 1959. The DC-8 became a highly successful commercial jetliner. Boeing developed the 707, which became one of the most successful commercial jetliners ever built. The 707 was powered by Pratt & Whitney JT3 jet engines. The 707 entered service in 1958. The 707 revolutionized commercial aviation by making long-distance travel faster and more efficient. The transition to jet-powered commercial aviation was enabled by the same jet engine technology that had been developed for military aircraft. The basic principles of jet propulsion that German engineers had developed in the 1930s and 1940s made possible the jet-powered commercial aviation that followed. Jet engine technology also contributed to the development of rocket engines for space exploration. The principles of jet propulsion that German engineers had developed involved burning fuel and oxidizer to create hot gases. These gases created thrust. The same principles applied to rocket engines. Rocket engines also burned fuel and oxidizer to create hot gases. These gases created thrust that propelled rockets. American rocket engineers studying German rocket technology and German jet engine technology understood the parallels. American rocket engines were designed using principles similar to jet engine design. American rocket engines used regenerative cooling principles similar to those used in German jet engines. The influence of German jet engine design on American rocket engine development contributed to American space achievements. The rockets that carried Americans to the moon used engines that incorporated design principles influenced by German engineering. The jet-powered Me-262 fighter aircraft and the Jumo 004 jet engine that powered it represented a revolutionary advancement in aviation technology. The Me-262 and Jumo 004 demonstrated that jet propulsion was operationally feasible for military aircraft. The Me-262 and Jumo 004 demonstrated that jet-powered aircraft had superior performance to piston-engine aircraft. The Me-262 and Jumo 004 showed the way forward for aviation development. When American engineers studied the Me-262 and Jumo 004, they learned invaluable lessons about jet aircraft design and jet engine development. American engineers incorporated what they learned into American aviation development. American jet fighters became some of the most capable aircraft in the world. The transition from piston-engine aircraft to jet-powered aircraft was one of the most important technological transitions in aviation history. This transition was enabled by research that German engineers had conducted in the 1930s and 1940s. This transition was accelerated when American engineers studied captured German aircraft and engines and applied what they learned to American aviation development. The capture of the Me-262 Messerschmitt aircraft and the discovery of the Jumo 004 jet engine marked the beginning of the jet age of aviation. Military aircraft transitioned from piston engines to jet engines. Fighter aircraft became faster and more capable. Commercial aviation transitioned to jet propulsion. Commercial aviation became faster and more efficient. Space exploration was enabled by jet engine technology applied to rockets. The entire trajectory of post-war aviation was influenced by the Me-262 and the technological principles it represented. American, British, and Soviet aviation development was influenced by understanding of German jet propulsion technology. Today, more than 75 years after the end of World War II, jet engines power military aircraft, commercial airliners, and space launch vehicles around the world. Jet engines trace their design principles back to the Jumo 004 engine that powered the Me-262 Messerschmitt. The Me-262 and Jumo 004 represented a revolutionary leap in aviation technology. When American engineers studied the captured aircraft and engine, they understood that aviation technology had entered a new era. American engineers worked to catch up to and ultimately surpass German jet technology. The result was a rapid acceleration of aviation development that transformed the world.